to take it.
You told me that it picked up one of your networking.
Yeah, that 440
yeah.
probably. Okay, so last time we were talking about some variable scoping issues over here, and then we started talking about reviewing some inheritance stuff. We're talking about some inheritance stuff. So if you remember correctly, we created a dumb fraction class, and the dumb fraction class extends fraction, which means it gets its own copy of all the stuff that belongs to the fraction class. And we saw that last time when we had our method or display method here, which we overrode. So rather than using the display method that we inherited from fraction here, we created our own more local version of the display method. We overrode that method, which prints out blah, but then it calls the parent's display method, okay, getting us back to the original one, which is this guy back here. And the parent's display method displays whatever this holds. And what's this? What's the this keyword? Pointer, which points to what? What memory address?
Whatever the object is that you are. It's how it refers to itself.
Yep, okay. So this is how this particular instance of fraction refers to itself. So this keyword here is this fraction's memory address. That make sense? And we saw that out here in driver when we created a fraction. We told the fraction to display itself, which prints out this. And then we went ahead and printed out whatever memory address f held. We saw they were the same address. So externally from the fraction class, we have a variable called f that points to this particular fraction. And f has that memory address. Internally, inside that fraction, we have a display method that prints out the address of itself. And those are the same address. So those are the first two lines that'll print here, these two guys. Okay? So this and f in this example are synonyms. This is how f refers to itself when it's inside itself and doesn't have access to that variable f. F is how we refer to it through the variable scope in driver where we have access to the variable f. Right here. Make sense? So that's what the this keyword is for. Now what we saw last time is we created this dumb fraction, which is a fraction. And a fraction is an object. And that created this hierarchy. Dumb fraction, fraction, object. So that means fraction has all the stuff that object has its own copy of all the stuff that object has, plus the stuff that we wrote to make it special. And what are those things? That's a numerator and denominator, this constructor, and a display method. That's what makes a fraction more than just an object. Okay? Dumb fraction gets everything that fraction has, which has everything that object has. That make sense? So fraction is a combination of these two things. Dumb fraction is a combination of these three things. So in dumb fraction, we have a new variable called is useless, but we also get our own copy of the fields, numerator and denominator. Dumb fraction also has its own constructor that just calls upon the parent's constructor here, passing a 1 and 1, because the parent's constructor takes two integers. And then dumb fraction also creates its own display method, which is said to override the method that it inherited from fraction. So dumb fraction's display method prints out blah, but then it goes ahead and calls its parent's display method. That is the method that it got a copy of from the parent. And we proved that last time. We proved that it was a copy because when a dumb fraction calls its display method, it's definitely going to print out blah. There's no question there. But then it calls its parent's display method, which prints out this. The question was, is the memory address this associated with a pointer to a fraction or the pointer to this dumb fraction? Does that make sense? It is the method that we inherited from our parent, from fraction. But does the keyword this refer to this instance of fraction, or is it as if this guy is copied into here? And this refers to this instance of dumb fraction. Does that make sense? So that's the question. We saw the answer last time was this refers to dumb fraction. See it out here. So right here we print out the address of dumb fraction, which is going to be some dumb fraction memory address. Then we call that dumb fraction's display method, which should display blah followed by a memory address. And that memory address will either be the fraction's memory address, the parent of dumb fraction, not necessarily this fraction, because when we created a dumb fraction right here, another instance of fraction was generated. Okay, so this df.display, when we call that, it's going to come into dumb fractions display method. It's going to print out blah, and then it's calling the display method that was inherited from the parent. So one of two things are going to display, either a pointer to a dumb fraction or a pointer to a fraction. Okay, that's going to tell us whether super.display is calling upon our instance of fraction, that is our parent, and asking that instance to call its display method, or whether we are saying that we want this particular dumb fraction to call the display method that it inherited from its parent that we overrode by writing our own display method. Does that make sense? So this guy, well, let's look at the punchline first. We'll see it's a dumb fraction. Okay, so there's our blah, the first line of our dumb fractions display method. And here's the display this, which you see matches the original dumb fraction. So these two guys match each other. So that means the this in that display method points to the dumb fraction that called it, not to the instance of fraction that was created as a result of creating an instance of dumb fraction to support this inheritance model. In order to create one of these, we have to create one of these, we have to create one of these. So there exists this fraction instance to support our dumb fraction. And this guy hands off all these things that belong to fraction to dumb fraction. But we chose to not inherit the display method and instead write our own. But then we saw that the display method still existed. We still had access to it by using the super keyword. The question we just answered is, are we actually asking the instance of fraction, that is our parent, to call his display method, or are we dictating that we actually want to call the display method that was copied to us locally from our parent? And we saw that it was the one that was copied to us locally from our parent because we got a dumb fraction pointer. So this was a dumb fraction, not a fraction. Okay? So the punchline there is that overriding a method does not destroy the inherited method. It hides it. Go ahead.
Why does it copy instead of why does it copy the method from the fraction class instead of you?
Well, let me see if I can guess at what you were going to ask. If you hear it, you think you'll know it? Okay. You want to know why they made that decision. Why did they choose to copy it rather than rely on the previous guy?
Right.
I think it's a fair question. They certainly could have gone the other direction, right? In which case, super.display would have functioned, but functioned differently. We would have gotten the pointer to that fraction object rather than the pointer to ourselves. So really, I think it's a design decision. Now, an interesting question here is this, and I think this will kind of answer it. What I'm going to do is we're going to say the display method for fraction sets this dot numerator. Actually, I'm not going to say this dot numerator. I'm going to say numerator is equal to 5. Okay? So when the parent's method that was copied to us gets called, it's going to print out the memory address of this dude, which we saw is already a dumb fraction, but then we're going to forcibly change the numerator to just a hard-coded value 5. All right? Now inside of dumb fractions display method, rather than printing out blah, let's print out numerator. And then let's print out numerator again. Okay? So numerator originally should be a 1, because that's what was created, right? Numerator and denominator are both 1s. Then we're going to call our display method, which prints out a memory address and then changes the value of numerator to 5. Print memory address, change the value to 5. We're not displaying it yet, we're just changing its value. Then we're coming down to dumb fraction, and we're displaying numerator. The question is, did this have a permanent change? When I didn't say this dot numerator here, I just said numerator, did it have an impact? All variables resolve to the most local definition, right? What's the most local definition of this guy? I'm already in the fraction class. It's this guy right here, right? So we don't have one in this local environment. We're not going to check this local environment because it's not linked to this one. So the next level up is this environment right here. That's the thing we talked about last time with this slide. These local environments, and then the global environment. So we'll change numerator to 5, and then we'll print out numerator again. So first dumb fraction, here's df, the memory address. Then we call that guy's display method, which prints out the value of numerator, which is a 1. Then calls the parent's display method, which we already saw prints out this, which is dumb fraction. And then it changes the value of numerator to 5. Then it returns to dumb fraction's version of display, which prints out the new value of numerator. Well, the value of numerator, which is the new value of numerator. Make sense? So, what if I come in here to fraction and I change this to this dot numerator? I come into dumb fraction and I change that one to this dot numerator, but leave the other one as just numerator. Okay? Will there be a change? Our gut feeling is no. Okay? And you're right, there won't be any change. Okay? What does that tell us already? That tells us that this dot is assumed to be here, whether we put it there or not. That make sense? Only because there isn't a local definition of display. I'm sorry, a local definition of numerator. If we had a local definition of numerator, actually, let's make this guy a 3. So this is in dumb fractions display. We'll have a definition of numerator, which we're going to set to 3. Then we'll display numerator. Then we call super.display, which is this guy, which prints out his memory address, then sets this dot numerator equal to 5. Then we come back here and we print out this dot numerator. What's going to display? Well, we're going to get a 3, because all variables resolve to their most local definition. Then we're going to get a memory address. Then we're going to get a 5. 3, memory address 5. As opposed to, what if I say this dot here? Now what is this going to display? Is that a guess or is that a? It's a guess. Anybody want to guess the other one? You think 5 and 5? Okay, well, this is the first place I'm printing out numerator, right?
Would it be 1 because you defined it up there inside of dumb fraction with super 1, 1?
You asking me or telling me?
Asking.
I want somebody to tell me.
Okay, I'm telling
you he's right.
Oh, you're telling me he's right. I believe he is right. Okay, so let's look at this. So we have a 1, followed by our memory address, followed by a 5. Why is this? All variables result to their most local definition. We have a local definition of numerator here, and that belongs to the environment associated with display. Now, if we just say numerator here, that variable will resolve to this version of numerator. But because we gave it the full address, because we said, I want you to get me the numerator associated with this instance of dumb fraction, it didn't even try to look here. Instead, it went immediately to the global level for this dumb fraction. And notice that we have a int numerator up here. We don't see it. Why? Because it was copied to us from here. Okay, so this gets back to your question of why did they choose to copy it rather than link it to the previous thing? Well, I think they have to choose to copy it to support the way that the this keyword works. Otherwise, the this keyword has 2 different meanings depending on how you use it, as well as the super keyword. Okay, this and super always refers to this particular instance, which means since we're inside of dumb fraction, this dot refers to this particular instance of dumb fraction. In order for that to be accurate and us being able to access the numerator variable of this guy, we had to have a copy of numerator given to us so that this dot numerator could resolve. Right? Otherwise, we're relying on it to convert this dot to super dot in the event that we didn't get the, in the event that we did not find a numerator up there.
So, question is, the instance of dumb fraction, is that what is in driver?
This in our dumb fraction is the same thing as df here.
But is that the instance of it?
Yes, this is the instance.
Okay.
So when we created dumb fraction here, inside of dumb fraction, a variable was created. Here, if I go ahead and I just steal this real quick. And I print out this, it'll be the same memory address. So there's our dumb fraction from driver. There's our dumb fraction from dumb fractions display method, line 1. This line right here.
I have a question.
Go ahead.
So if you have integer numerator equals 3, and then system.out.println this dot numerator. Now let's say you don't have a class fraction, like there's no parent, there's no extension.
Okay.
Would it resolve to 3, or would it?
All right. So you wanna dump this connection.
Right.
Okay. So we're gonna dump that connection. Notice that this dot numerator doesn't exist. It tried to go up here and look for one, but it didn't exist. And actually, it's a good question you asked because it proves what I was just saying. This dot numerator works in a very specific way. It immediately goes to the top level variable environment associated with this instance of the object, whatever object we're in. Okay? When I say this dot numerator without extending anything up here, it literally is going to look at this parameter list or this list of variables up here, and we do not have a numerator defined. It's not there. We can clearly see. Well, let me take the comment down so we can definitely clearly see. There is not a numerator there, right? Okay, not there. Now, we happen to know that in fraction, we did build a numerator and denominator. But we don't have access to that from fraction right now because we're inside of a dumb fraction. And as we have it written right now, dumb fraction and fraction are not linked to each other in any way, right? These, just by their name, dumb fraction and fraction kind of seem similar, okay, but they're not actually linked in any way. When we come up here and we say extends fraction, now this dot numerator works, but it doesn't work any differently than it worked 10 seconds ago. It's still doing the exact same thing. What happened is it now actually found that variable up here because that variable was copied into this version of fraction from its parent. And that kind of supports what I was saying back here. When we create a dumb fractions are defined in terms of all three of these things. That makes sense? Everything from object gets pulled into fraction. Everything from fraction, including the crap from object, gets pulled into dumb fraction. We can hide some of those features by creating our own more local copies, but we will still be able to get to the more global copy through the super keyword. That make sense?
So copying everything includes variables, methods, everything?
Mm-hmm. Yeah, all class members. So classes are comprised of what three things from last semester? Try to use the correct object-oriented terms. You already said two of them, so say them again, but say one of them more better.
Variables.
Say the variable one more better.
Global.
Maybe a German accent or something. What are top level variables?
Global.
That's not an untrue statement, but it's not the object oriented term for that guy. I've already said it once in class today.
Object.
No, this would be the object. Name of the class is the object. Here we'll cover the other ones first. Kind of animal is this guy?
Constructor.
Why is it a constructor?
Why is it a constructor?
Yep, constructor's right. So since you got the answer wrong, you get to tell me why it's a constructor.
Is it because it's building something?
Well, that's what it does, but you don't necessarily know that. You're just making that up. Just by glancing at what I have highlighted, how do you know that's a constructor? Two facts.
Static isn't it?
Nope. I suppose that actually is a true statement because static will never be in front of a constructor, but that doesn't tell us what it's a constructor. Let's see if we can really embarrass you now. Let's see if he knows the answer.
Oh, come on, you're trying to embarrass me, actually.
By the way, I'm stepping through stupid people. This is par for the course. I know you've been happy before. All right. See, do you know her? All right, we'll go back to him. Got nothing. Why is it a constructor?
Because it's the same name as the class.
Same name as the class. So notice dumb fraction, capitalization and everything is the same exact name as the class. That's first rule of thumb. It's a constructor if it has that. Okay? Secondarily, what's the other thing that we know, how we know it's a constructor, assuming it's legal code?
The super one.
Actually, that's probably fair. This isn't required, but that is probably a fair statement. If you do see this syntax only works inside of constructors. Not what I was thinking, but a true statement. So what's the other reason? It has to do with the difference between this guy and this guy. There's a subtle difference between those two.
Void. Makes
Okay.
it a method.
The void makes a method. Why? What is void? It's a return type. We don't have a return type here, right? Constructors never have a return type. So the two identifying factors that make something a constructor has the same name as the class, case sensitive and all. Okay? Capital D, capital F in this case. Java is case sensitive. So same name as the class and no return type. Why does it not have a return type? I'll take us over to this screen for that hint. Here, I'll highlight the line that gives you your hint. Why do this is where we're calling the constructor, right? Right here? Okay. Why do constructors not have a return type? We saw it defined in the other file. Now we're seeing it used here. Go ahead.
Because it's already set and right there, it's like already like defined as like the variable is going to be. So like there's no return type for it. You don't have to put it because it's already there.
Well, clearly you don't have to put it because it's worked all along for us by not putting it. Okay, but what do you mean by it's already there?
It's like associated with it. You defined it.
It's built into the constructor.
Would you say, well, that's also true. That's why we don't have to define it. But why? Is this a constructor up here? Okay, that's us calling the fraction constructor. And if we jump into the fraction class, we'll see that the constructor for fraction, that guy's the constructor. Name fraction, same name as the class. So past step one, right? Past rule one. Rule two, no return type. Must be a constructor, right? This particular constructor requires two inputs. So when you see us using it out here, you see us passing the fraction constructor two integers. But you see us passing the dumb fraction constructor nothing because dumb fraction told us it didn't require anything to work. Okay? So out here in the wild, we are seeing two separate constructors called. And we know that at the definition, we just looked at both fraction class and the dumb fraction class, that the definition for those constructors in both cases omit a return type. What is the return type of a constructor? Well, that's not incorrect. Well, it is incorrect, but it's not wrong. An instance is produced as the result of calling constructor. An instance is built. Okay, an instance is built. We created a fraction and a dumb fraction here. What printed out right here?
The memory address.
What printed out right here?
Memory address.
Memory address. Okay. So the value. So remember, the generic syntax for a variable is type var name equals value. So whatever's on the right-hand side of this assignment operator resolves to a value that is stored in this variable name. That makes sense? We know, well, we proved that the value stored in F is a memory address. The value stored in DF is a memory address. Both of those guys point to instances of those objects that live somewhere in memory. Okay? Just like if I had hired a constructor to build me a house, and then he's going to give me the address of where I can go find my built house. The house is the instance. The address is where I can find it. Okay? These guys are printing out addresses. Well, again, these constructors do not have return types. Why is that? What do those two lines have in common? New keyword. Tell me about the new keyword.
It goes and gets you a new memory address.
Yeah, so our real estate agent goes and finds us a plot of land big enough to hold one of these dudes. And one of these dudes. Right? So, is there ever a situation, as far as you're aware, where we call a constructor without the new keyword? To your recollection, have you ever seen that happen? No. We always call constructors using the new keyword. And the new keyword always produces what? Memory address. Always, 100% of the time. New keyword makes memory addresses. Constructors are always called with a new keyword. Constructors are always on the right-hand side of the assignment operator. So that means the assignment operator, on the right-hand side of the assignment operator, when we're calling constructor, it's always the word new, followed by the constructor, followed by whatever parameters are required. So the right-hand side here always produces a memory address. Correct? A pointer to where that particular instance lives. So, over here in dumb fraction, we don't need a return type because the return type is always a memory address. It's always a pointer. And Java has abstracted that for us and said, why should we make you create a pointer return type when it's always that? It's a waste of time. It's also an impossibility in Java because Java doesn't support a syntax for pointers, right? Remember last semester when we first talked about pointers? I made some comment about, hey, you know, most textbooks, Java textbooks talk about pointers not existing in Java, which is crap. We've seen pointers printed all over the place today. Pointer, 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 pointer. We have 7 lines of code and 5 of them are pointers. Okay? Pointers exist in Java. We just don't have a specialized syntax for pointers like we do in some older languages. Okay? So one of the benefits of Java, as well as in my opinion one of the weaknesses from a teaching language perspective, is that Java hides many things from us. For instance, we saw it hide extends object. That's not required. That's there for us, right? Similarly, Java hides the return type for the constructor because it's always going to be the same thing. If every single object that we create that we don't choose to inherit from something else automatically inherits from object, why should we have to write it? If every single constructor returns a memory address, why should we have to write it? That makes sense, correct? Why waste our time writing something that never changes? So logically, that makes sense. Educationally, we miss out, but I've reinserted it into your knowledge base now, but educationally, if you were just looking at this, you miss out on those details because they're hidden from us. Does that make sense? It's actually one of the reasons I like, from a teaching perspective, a language like ObjectiveC, which is the language that we do Mac development and iOS development. It doesn't hide many of these features, which after the fact you might say, well, why not? The modern language, why doesn't it hide this crap? If the return type for a constructor in Java, or I'm sorry, in ObjectiveC, this would be written as actually, it would probably look like this. Init with numerator something like that would be what the header of this looked like in ObjectiveC. So that line and these 2 lines are equivalents in these 2 languages. So notice in ObjectiveC, the constructor name doesn't necessarily have to match the class name. Because in ObjectiveC, the constructors and methods are indistinguishable. They both have return types. So there's nothing that is different about a constructor than a method in ObjectiveC. The return type for this guy is ID, which is a generic pointer in ObjectiveC. Okay? In an older language like C or C++, this might look like void pointer. That would be the specialized syntax for a pointer. That's a generic pointer. All right? But we've seen here that that's never necessary because the language should be smart enough, the compiler should be smart enough to create our low-level language with the correct types because it's always the same type. That makes sense? So I like in ObjectiveC that it forces us to remember this. Similarly, if I just keep going with this example from ObjectiveC without actually opening up Xcode and writing this, I'll just put it in a big comment. So if I'm implementing this constructor, similarly, let me actually come up here to the top. We would have public class fraction extends NS object. So this is equivalent to saying extends object in Java. This is required in Objective-C. We have to have the extends object in there, even though in Java we don't. Not required. Okay, so go ahead.
It just wouldn't recognize it as an object then?
Correct. Yeah, it would actually either give you an error or say struct not found. It depends on. It certainly would have said struct not found in an older compiler. It might just give you an error now. So this is required, to support the way object-oriented languages are built. I'm telling you that every object-oriented language functions around this idea that you must have an original object and everything inherits from that, but may inherit from other things. So the class would look like this. The constructor header might look like that. The very first line in every constructor in Objective-C would look like this. The very last line would look like that. Self in Objective-C is equivalent to this. That's the this keyword in Objective-C. So in Java, if we look at a constructor, we're not defining the value of this, are we? But we know what happens. We know that this gets created because we've printed it out a bunch of times today. Java does it behind the scenes for us. In Objective-C, we have to take our variable self, which we inherited from NS object, and we need to give it a value. What value are we going to give it? We're going to call our parents constructor, which is called init. So that's objects constructor, which has the magic in it to create that initial memory address and generate an instance for us. So self gets a value there. Then we do anything special. Well, here we probably say something like numerator is equal to n, denominator is equal to d. Then in the end, we return self. That is a pointer back to us. Does that make sense? That's where that memory address came from. We generated our memory address here. We return it right here. It comes firing out as a generic pointer. Now, this is definition. If we want to see that guy being used, we might say fraction f is equal to something like that. So this is allocating memory for a brand new fraction. Then we're calling the constructor a init with numerator, which takes an integer and another integer. That's the first integer, that's the second integer. So we're passing in 1 and 2 for 1/2. The constructor does what? It creates our value for this, value for self, initializes our, you're going to tell me what the name of that is in a second. Okay, our variable is known by a more proper name in object-oriented speech, and then ultimately returns that object, that memory address. So you see how much is hidden from us by Java? Which is okay. Java probably does a better job. Why write all this crap if you don't have to? But we should still know that it's being done, because it shows us a lot of what's happening under the hood. Make sense? All sorts of really good quiz questions come out of this kind of crap. All right, so now you were saying about if I asked the question, what components are the members of a class? You told me about constructors. Agree with that one. What else? So this guy, you said is a constructor. What's this guy? Method. Constructors and methods. Okay? Well, the other things we see here are these guys. What are those guys? Fields. Did you look that up or did you remember it? No, that's okay. Okay, those are fields. So objects are made up of, the members of an object are fields, constructors, and methods. Okay, we can have 0 or more fields. Fields are top-level variables, global variables to the object. So for instance, if I come down there and create this local variable inside the display method, that is not a field. This is just a local variable whose scope is within this method. Fields are at the top level of an object. They don't have to come first. We could define our fields in between these guys or at the very end. Traditional code organization has fields defined at the very top. But they can be defined anywhere inside of this opening curly brace and this closing curly brace, provided that they're not defined inside of any methods or constructors. Okay, so we have fields. We have constructors. We can have 0 or more constructors. If we don't provide a constructor, one will automatically be created for us that does nothing except support this syntax. So if we don't specifically define a dumb fraction constructor, it'll create one that looks just like that takes no parameters, strictly to support this syntax right here to make it work. Okay? We'll never see it written. It won't show up in our code, but it'll be there. Now, if we do write a constructor, for instance, for fraction, we wrote a constructor, correct? 1/2. Takes 2 parameters. Because we wrote a constructor, the no argument constructor was not created. So for instance, if I say fraction f2 is equal to new fraction, that's an error. Okay? Because we chose to write our own fraction, we were not provided with this default no argument one. Make sense? We only get the freebie constructor if we choose not to write a constructor. And that freebie constructor does us no good except to support that syntax, to make that work on this side when we're creating those objects. When would you choose to not write a constructor? Does it ever make sense not to write a constructor? What's the job of a constructor? What's its purpose?
To create the instance.
Okay. Fair enough. What's involved in creating an instance?
Assigning the values to the fields.
Okay. Assigning values to fields. What if you don't have any fields? If you don't have any fields, do you really have to do anything? Another way of putting it for what a constructor does, you might say the job of a constructor is to initialize the fields associated with this object. Okay? Do any initialization to build this object. If you have no fields, or it for whatever reason isn't appropriate to initialize those fields to values, you don't need a constructor. I would say you should never have a constructor that looks like that you wrote yourself. Doesn't do anything. Why not just let it create one for us? This guy's screaming at us because a dumb fraction is a fraction. and it has some fields that were inherited that we're not initializing. Oh, we can fix that. Let's just not make it extend fraction anymore. No problem. But now this dot numerator breaks. The super dot display breaks. We don't have access to a parent anymore. Well, we actually do have access to a parent. Who is this guy's parent now? Object. And if this guy's underlined in red, what does that mean? Object doesn't have a display method. We checked. No display method. Okay? Object has these methods. Get class, clone, toString, equals, blah, blah, blah.
So, question quick.
Go ahead.
We're creating a method called display right there. If you do this dot display, would it break due to recursion?
Inside here?
Yeah.
Oh, it would. That's an interesting point. So you want to do something like this. So we'll display this and then say this dot display?
Yeah.
Yeah. Yeah, it's going to end badly. So when we call our display method, we're going to print out our memory address, and then we're going to call ourselves. That is the display method owned by this object. What does that display method do? Prints out the memory address, then calls the display method. What does that display method do? Prints out a memory address, calls the display method. Okay, so do you remember what error you'll get from this? It's close. We did that in dumb fraction, right? We do that in fraction. Dumb fraction. Okay. So we create our dumb fraction. Notice that we did not write a constructor in dumb fraction, and it's not yelling at us here. So that no argument constructor that does nothing was created for us. What's the output of this going to be? And what's the error message we're ultimately going to get? Okay, we're going to get just one memory address, a bunch of them until something bad happens. It will be an endless loop, but it actually will eventually throw an exception. What will that exception be? Do you remember? We looked at it last semester when we looked at recursion. It was actually very related to this class. We'll have a stack overflow exception. Recursion in most languages is implemented in terms of a stack data structure, which we'll learn about here in the first couple weeks of this class. There's our stack overflow. So every instance of the Java virtual machine is given a certain amount of space in the stack to support recursion. And, well, support recursion among other things. And if we write infinite recursion like that, eventually we run out of space. And instead of your program just crashing, it gives us a little error as to why it crashed. If we were dealing with an older language like C or C++ that has direct memory access, very, very possibly that program would have caused us to have to reboot our computer. It would have taken up all of our system memory. It's one of the advantages, if you will, of working within a virtual machine, that the worst that could happen is the virtual machine crashes. No biggie, you just run the program again after you fix it, right? But if you're running it on the actual machine, like a C and C++ program, now you can crash the actual machine. And you're sharing that RAM with the operating system, with instant messenger, with email clients, with Word. You're sharing memory with all those things. All of a sudden, you're taking up all the rest of the free system memory. All right, that makes sense? Okay, so that is the inheritance model and kind of how it works, and also an example of little bit more example about pointers. Pointers are going to be a very important part of what we're doing in this class. So, public, private, protected. These are, let me do it with this, keywords which dictate how class members are used internally, well, actually, let's say are used externally. Maybe it's not external, it's just external. Use external to the class. Close enough. Okay, public, private, protected are our three options. If you put nothing, it's actually package level security. But you can't actually use that keyword. That's just the default. All right, so let's talk about these for some examples. Go back into our fraction class. Notice we've already used some public stuff here. We'll talk about that in a minute. But our fields, where this is likely most important, but it's important throughout. Our fields here, we have no special keywords in front of it. So this indicates that it is the default package level security, which means these guys are accessible anywhere in the package that this file is defined, which is by default in Eclipse the default package. Okay, so that means if we are in driver or dumb fraction or fraction itself, if we were to create an instance of fraction, we have direct access to numerator and denominator. And to show you that, there's my instance of fraction in driver. I could say, even though I passed it in a 1/2, let's just go back real quick here. We'll make our display method for our fraction kind of show a fraction-y looking thing. Okay, dumb fraction is not even in play right now. We're not messing with that this second. So I create a fraction and I say f dot display. This is going to display the fraction 1/2, right? Like this. Okay. Now what I can do though is now I can say f dot numerator is equal to 13. I can directly modify that field that's associated with f, because driver belongs to the same default package as fraction did. So now if I say f dot display, we have a brand new fraction. I permanently modified that object, external to the object, because of the way I defined those fields. Because I made those fields protected, I'm sorry, not protected, because I made them package level by not putting anything in front, I have access to them anywhere in the package.
So it permanently changes the what?
In this case, I permanently changed the numerator.
And what's the numerator? The variable?
Yeah, inside fraction. This guy right here. So one of my two fields in fraction is numerator, and I set the numerator through the constructor right here. But because I didn't put any sort of security on these guys, I was able to directly access the numerator and modify it outside of the fraction class. That make sense? Okay. we think about this in a real world example, a lot of times we don't want to modify the internal workings of something haphazardly. We want it to go through some sort of checks and balances, right? So for instance, what if you're, and just even take this to the next level up. Let me just make both of these public. And now both of those guys are public. That means they're accessible anywhere, not just in the package. They're accessible anywhere. So public class members are accessible anywhere. That can create an instance of the class. That's the most accurate definition. If you can create an instance of the class, you can access those class members. Okay, so we'll say that I've made them public now, so now they're even more exposed than they were a second ago. But from our perspective, they're the same level of, they have the same level of exposure. We can still do what we did over here in driver. Create our fraction, tell our fraction to display itself based on the initial values of numerator and denominator. But then we can change one of those values without any oversight and then show that we've actually modified that fraction. Okay, real world example to this. Most of us have bank accounts, right? We probably all wish we had more money in there than we did, but let's say you have $100 in your bank account. And I was able to go and take the $100 out of your bank account, put it in my bank account without you knowing about it. Would you be happy about that?
No.
Okay. We'd like there to be some level of security on our bank account. We only want us to be able to control how our bank account balance has changed. That make sense? Okay? Treat this like a bank account. I would say good programmers always make their fields and methods, always make their class members as private as they possibly can. So I always recommend that you start everything off as private and then loosen the reins as needed. Okay, so let me give some definition to private. Do we kind of understand now the purpose of these things? Okay, I think the bank account's a pretty good analogy. Okay, so we start everything off as private. Private class members are accessible only within the class they were defined. Okay? Class members are accessible only within the class that they were defined. Notice out here in driver, since I made numerator private, I can no longer access it from driver. Why? Because driver is not class fraction.
So if we go back into dumb fraction and that extends, or you make it extend fraction,
Yep.
Does it copy over those still, even though they're private?
We don't have access to numerator in here. Why? Because dumb fraction is not fraction. These guys are private. Make sense? So making a class member private means it is only accessible within that exact class. So if you're not inside the class it was defined in, you can't access it. If we make these protected, notice that now dumb fraction does have access to it. So protected actually does a couple of things, but from our understanding, I think the most important thing is that a protected class members are accessible only within the class they were defined and children of that class. So the most private that we can make the class members, numerator and denominator of fraction, is protected if we want them to be accessible by things that extend fraction. But notice that still works. This is that caveat thing. It's because we're sitting in the same directory. Okay? But in terms of our understanding, I would suggest you pretend that's an error. Okay? You would not want to think about it working like that. Okay? Typically, when you're writing professional level software, you're going to pay a whole lot more attention to the packages and the directory structure of your code. In our case, we just kind of throw everything into the same default package and throw everything in the same folder and just say, this is good enough, okay, because of our level of understanding. So realistically, we would put these guys, dumb fraction and fraction, inside of their own package and have driver sitting external to that. Okay, so the reality in this particular language, protected is a synonym for package. Okay, these two guys are the same. Now, in older languages, like C++, I'll just write it on the next line. C++ has a security thing called, is it friend or friendly? I think it's friend. Called friend. And this is package level. So anywhere inside the same package, which is a synonym for what protected is in Java, because this concept of package relies on how you've organized your code. But from our perspective, the understanding I like to think about when I'm teaching this is protected is how you expose a variable to the children of a class. Private is how you keep it only within the class it was defined. Public is how you make it accessible to everything in the package, because we're working within the package. You know, we have our default package that we're doing most of our coding in.
So can you create multiple packages?
You can.
inside of a project?
Yeah, you can, and kind of the evidence of that, and that's actually how Java kind of works. If you come up here, and like last semester, we were using some things from the java.utils library. If I say import java.util, notice there's sub-packages within util. So java.util.star gives me everything that's in util. Java.util.concurrent .star gets me everything in there, but concurrent .whatever allows me to access atomic and locks. So the normal organization of the Java language has this hierarchy of packages. From our perspective, we really only start running into those when we start writing more complex applications.
Why wouldn't you always do import.util.star if that gives you access to everything?
Well, it makes your executable larger. You know, so if you, import java.util just has the utility stuff like scanner that we've used and string tokenizer, that kind of stuff. So let's just say there's 100 things in there, okay? And we need 3. Well, if we import all of them, that means we're essentially bringing 100 different .java files into our package. And that gets locally compiled for us, whether we use it or not. Does that make sense? Realistically, the lazy programmer just imports everything and says, we'll let the compiler deal with it. You know, chances are the modern compilers that have gotten pretty good probably going to notice you haven't used a bunch of those and unlink them. The benefit, and if you notice, like for instance, if we go ahead and I create a scanner input is equal to a new scanner system.in, something like that, it's yelling at me and I hover over this and it says one of the fixes is to import java.util. It'll say java.util.scanner. Okay. One nice thing about organizing like this is you can go up to the top of your code and see the different tools this guy's using. Now let's say that we decide later on, oh, let's get rid of scanner. We're not going to use that there. All of a sudden you'll see this guy show up as yellow up there, telling us, hey, you've imported this thing, but you're never using it. Okay, so it is giving you kind of a little checks and balances thing about what type of crap this works with. And just to kind of give you an idea of maybe a real world example of this, let me pop open let me show you one of my larger projects. So this is an iPhone app. So it'll pop it open, and this app uses a cloud resource called Parse. And let's find a good example here. Well, this is good enough, I guess, for this example. So this guy, don't worry about this top line here, but this guy brings in this imports the main parse library and also imports these Facebook things for using authentication through Facebook. Now those guys themselves, actually, this is kind of what a linker does when it brings those libraries in. In Java, you have to do this, in ObjectiveC, you have to do the importing yourself. So notice that it's showing me I'm not using these specific frameworks here. But here's the parse framework and some other things. So these are things that I am using. So all these little yellow things here are frameworks that I'm currently using in my code. I had to go through and as part of the build process here, link these binaries in. Does that make sense? Okay, so kind of an important thing. These are actually used in my program, but I do the development for this on a different machine. And they're local libraries. They only get built into the executable when I actually compile and release it for, build it for release to send it out to somebody. So then they get actually packaged with this thing. It's called the bundle, but whatever. But here's kind of that example where you have all these external libraries that kind of play into the things that your code uses. And I can go in, if I want to add another library here, I can go hit this little plus sign, and here, I can use the accelerate framework. I just brought, maybe that's a 20 megabyte framework that I bring into my program that I don't even use. It's wasteful. Makes sense? Ends up making your executable larger than it needs to be. Less of a big deal today than probably it ever has been, just because our internet speeds are pretty quick, and if your size of the app you're downloading is 6 megabytes instead of 4 megabytes, we're not going to notice probably. But historically, certainly these things were, if you had to have a program that would fit on a floppy disk, this would certainly come into play. Close that because I don't want it to auto open next time. All right, so punchline is probably only import the stuff you need. That's the conscientious programmer type thing to do. Okay? So do we understand the concept of public-private protected? Okay, now let me quickly jump into Angel. structures. We're getting ready to start looking at data structures. And on Angel, you have this textbook I've given you. I'll go ahead and just open it in here. All right, so notice this first chapter of this guy deals with an introduction to data structures. All right, so what I want you to do for Tuesday is read through chapter 1 of this. This kind of gives you some background on data structures. It also talks a little bit about design patterns, which will hopefully be consistent with some of the things I talked about last semester. If you're looping through everything of a string, you have a pattern. We have our for loop for looping through a string, right? We start seeing repeating patterns in our solutions to stuff. Design patterns talks about this at a little bit more formal level. But really, when I'm at the part of this that's most important, the part of this that's probably most likely to show up on a quiz, if I were to ask you a quiz, is really this first part here, philosophy of data structures, why do we need them, and the costs and benefits, because this is going to talk a lot about the memory, okay, stuff that we really care about in here. We'll discuss this on Tuesday. This is kind of where we're going to start our discussion on data structures. Abstract data types and data structures, this is good too. That's all part of that first section. Design patterns, interesting read, but if you were going to half-ass this and skim something, do that section, okay? Well, I'm a realist, you guys know that. So, the real meat here is this first part, okay? These last pieces are more just kind of the conclusion. You have the conclusion of a chapter, and then you have the summary crap, okay? So flip through that too. I'd recommend you read all of it. It's only 20 pages, but really section 1.1 and 1.2 is what I might throw a quiz at you from, okay? Make sense? All right, see everybody on Tuesday.